2 minutes. Okay. Hello, everyone, and welcome to the NCCR Automation Seminar Series. So before that, I would like to thank our two speakers today, Professor Dorsa Sadigh and Erdem Biyik from Stanford University. They joined us in a very early morning in California, so thank you very much. The title of the talk today that will be shared by Dorsa and Erdem will be Interactive Robotics Through the Lenses of Learning. And before giving the floor to them to start, I would like to introduce our speakers today. So Dorsa Sadigh is an assistant professor in computer science and electrical engineering at Stanford University. She received her PhD in electrical engineering and computer science from University of California, Berkeley in 2017, and her bachelor's degree from the same university in 2012. She has received numerous awards, such as the NSF Career Award, the AFOSR Young Investigator Award, the IEEE TCCPS Early Career Award, MIT TR35, among others, and multiple industry awards, such as the JP Morgan, Google, and Amazon Faculty Research Awards. So Erdem is a PhD candidate at the Electrical Engineering Department at Stanford. He received his MSc degree from Stanford in 2019 and his BSc from Bilkent University in Turkey in 2017, and he also worked at Google as a research intern in 2021. So thank you very much for joining us today, and please, the floor is yours.
All right, yeah, thanks a lot for inviting us. Really excited to be here, and thanks for the kind introduction, Vahid. Really excited to share with you guys some of the work that we have been doing. So let me just share my screen real quick. Everyone can see it. Okay, thumbs up. Yes. All right. Yeah. So, I'm Dorsa, and today, along with Erdem, we're going to talk to you a little bit about some of our work in the space of interactive robotics. And in general, my research is at this intersection of machine learning and control theory, and bringing ideas from machine learning and control theory, particularly to the application of robotics and human-robot interaction. And today, what I'd like to do is I'd like to spend a little bit of time talking about how we can learn from interactions with humans or robots interacting in the world in generally, and then how can we build robotics agents or control algorithms that can actually be a lot more interactive, collaborative, coordinative, or even competitive. And what I'm going to do is I'm going to spend the first half of the talk talking about these algorithms that are like more coordinative and collaborative. And in the second half of the talk, Erdem is going to talk a little bit about some of his work in the space of active learning, where we are trying to learn from interactions with our world or from interactions with humans. Also, a side note, Erdem is on the job market this year, so I just wanted to put that advertisement out there too. All right, so let's just get started. So if you think about the field of robotics, over the past decade has seen a lot of advances, and a lot of these advances are due to control theory. So the robot on the left is from Boston Dynamics. They use really fancy controllers, and the robot can do these parkour maneuvers, which is pretty amazing. And then a lot of these types of advancements is due to machine learning. So on the right, you see the OpenAI arm, and they're basically trying to move this block from one configuration to another. And reinforcement learning plays a huge role in actually getting this robot to do these types of maneuvers. So robotics has seen a lot of advances, and that allows us to finally start thinking about robotics agents interacting with us and working with us in our everyday homes. We're starting to see these in our cities or in our homes. Examples of these are things like autonomous cars interacting with pedestrians or human-driven cars. Actually, Waymo has started driving their cars in San Francisco. You can actually like be in the beta program and get a Waymo car and get in the Waymo car to go to your destination. And that is pretty exciting. But other examples, like even beyond autonomous driving, are examples of robotics agents in homes helping people in service settings or in assistive settings. For example, these types of robot arms on wheelchairs are actually commonly used by people with disability for their everyday tasks, like moving objects around, putting clothes on, feeding themselves. So that's really exciting, but that basically tells us that we need to have good models of how these agents interact with humans and how these agents should learn from those interactions with humans and build better control systems. So how should we go about that? And I want to spend a little bit of time thinking about that interaction problem. So one very common way of modeling interaction is to think about how two humans interact with each other, right? Humans are amazing at this. They easily come to each other's spaces and they collaborate and coordinate with each other on very complex manipulation tasks. And a good question to ask is, well, how do they do that? Like, how do two humans coordinate? And I'm always amazed by looking at how two humans can seamlessly work with each other without like any need of like building like high dimensional policies about the other agent. But one very common way of modeling this interaction is to say, well, I have two humans, they're trying to do a task together. It could be a competitive task or a collaborative task. Maybe they're trying to play a game of chess. And they probably have some sort of model of the other agent, some opponent model that they're trying to keep track of. And in that opponent model, they might even capture the fact that the opponent is also modeling them. And then they capture the fact that the opponent knows that they're modeling them, modeling about them. And this kind of has this game theoretic type of interaction between the agents. This is oftentimes referred to as theory of mind, this recursive belief modeling. And there's kind of like an infinite regress here, which could be handled by solving the equilibrium of this game, this two-player game. But also in general, like this type of idea, like tends to be very computationally expensive, right? Like if I want to solve that game at every time step, that ends up being computationally pretty challenging. So instead, every field that tries to use this idea of recursive belief modeling or theory of mind, they try to approximate the game. So instead of solving the full game, what people often do is they cut the game at some times, at the first time step or second time step and so on. So this type of approximation, it actually commonly shows up in a lot of human-robot interaction work. So when we think about humans interacting with robots, well, we need to model the fact that the human has a model of the robot, has a representation of the robot. Quite a bit of work goes into this category of things. But then we also need to capture the fact that the robot tries to have some model of the human. And actually in the second part of the talk, Erdem is going to talk a little bit about this component. How do robots build models of humans? But let me talk a little bit about this interaction. So once we have this model, right, like we approximate it, and then we can go ahead and solve our game and build interactive agents using this game theoretic type of perspective. And we have actually like done that in the setting of autonomous driving. So a couple of years back, what we basically looked at was the interactions between autonomous cars and human-driven cars. So the idea is that if I have an autonomous car, that's the orange car here, and if that orange car wants to interact with a human-driven car, the white car, I can model this interaction using this game theoretic type of model, and basically say, well, the actions of the autonomous car, the orange car, is going to influence the actions of the human. So the way to model that is to say that the autonomous car is trying to follow a policy. That policy is, let's say, UR star. That's an optimizer of some sort of objective, reward function, or minimizer of some cost function. And that reward function is a function of states and actions, which is usual, which is what it usually should be. But then we say, well, this reward function should also depend on what the human does, that model that we often capture of how is this opponent. In this case, it's not really an opponent, but it's just another car that we are interacting with. But we need to have a model of that, and I'm going to represent that by this UH star. And a very good question to ask is, well, how do humans act here? And the way we model humans is by saying, well, humans are approximately optimizing their own reward function, RH. And that reward function is a function of states and actions of themselves and actions of the autonomous car. So you kind of see that two-player game, that recursive belief modeling here, right? There's a nested optimization here. The autonomous car depends on the actions of the human depends on the actions of the autonomous car, but we approximate this game, we solve it as a stackable game by cutting the game at the first time step and using that approximation as a way of going forward. There are also a lot of other interesting questions here that I'm not talking about today. So specifically, is this a right model of how humans act? Like is it okay for me to model humans as reward optimizers? is that true in all scenarios? Like we actually have some set of work where we are looking at near accident driving scenarios and the fact that humans are not always optimizing a simple reward function when we are in near accident scenarios. Another interesting question is a reward design question. So if I have an autonomous car, what should be the reward of that autonomous car? And that's a very difficult question that car companies like struggle with even today. Like, how do I balance between safety and efficiency and comfort? And we actually have a set of work that tries to address that question that, again, I'm not talking about today. But the thing I want to mention is that this game theoretic model, under some assumption of the reward of the robot, under some assumption of modeling the human, kind of works. So we were able to show that using this modeling, like modeling the whole system as a dynamical system, as an underactuated dynamical system, allows us to get the autonomous car influence human-driven cars in ways that are interesting. For example, we were able to get behaviors, interactive behaviors, where our autonomous car basically start like nudging in front of another driver to make room for itself when it's trying to change lanes. And that's very interesting because my autonomous car, let's say that the white car is my autonomous car by nudging in, it influences the human-driven car, the black car, to slow down and make room for it. And that is the result of this game theoretic modeling. If we don't do that, like we end up in scenarios that kind of look like this. So this is a video of a Waymo car from a couple of years back. It wants to change lanes. It's in an exit lane, so it has to change lanes, otherwise it needs to exit. It starts signaling, so it's doing everything like based on the rules of the game, like it's doing everything right, but it's not acting in an interactive or assertive way in any ways. It doesn't consider the interactions that I was talking about. And because of that, it's actually not able to change lanes. It needs to exit and come back around and try again, which is not very ideal. So instead, with this game theoretic type of modeling, right, like we could actually like think about interactions in a more careful way. So I've been talking about this idea of modeling the interaction using theory of mind as one particular way of thinking about interactions, one necessary way of thinking about interaction. And I would also like to argue that for a lot of tasks, we definitely like need that even for functionality purposes. I think one mistake that autonomous driving car companies made for the longest was they didn't think about behavior modeling as a first step. Like a lot of car companies didn't even have a behavior modeling team until very recently. And at some point they realized that worrying about the functionality of autonomous car is not enough. Like you need to think about interaction from ground up, because otherwise you get those behaviors of the Waymo car that I was showing you earlier. But the thing I want to talk about today a little bit is actually not theory of mind and this game theoretic modeling. I would like to talk about an orthogonal perspective to this theory of mind modeling, which I also think is useful as useful as theory of mind in a lot of other types of collaborative or competitive settings. And the reason I want to talk about that is I'd like to argue that there are many interactive tasks that are not like playing chess, that don't need this theory of mind modeling. Here's an example. So imagine I have two people, Alex and Bob, coming together, and Alex and Bob are trying to build some sort of structure together. So in this setting, I really don't think Alex here is thinking, well, I wonder what Bob's belief of my policy is, or I wonder what Bob's belief of what I'm going to do next is. Instead, like they're able to capture the right representation about the task or about the partner that is sufficient for coordinating on the task. It's almost like a sufficient statistics that is needed for coordination. And people are amazing at just capturing that. Like they figure out like, oh, maybe I need to figure out if this person is pushing or pulling, or like if they're leading or following. And then again, we often have names for these things. Maybe we call it intent. We need to figure out what is the intent of the person. And at this point, you might say, well, what is the big deal, right? There's a lot of work that tries to do belief modeling over intents. Like we have known that intents are important and we need to do belief modeling over intents. But the thing I'm arguing here is not to do belief modeling over intent, but instead to directly figure out what is the space of things that we call intent. Like what is the space of representations that, again, people are really good at capturing, and could we find those like automatically, and could we do belief modeling over that space without like me predefining like 5 intents or predefining 3 driving styles, which is something that like we used to do in our prior work. But I think this work is interesting because it's not making any hand-coded predefined assumptions about that space. All right, so that kind of like brings me to the key insight of this work that I'd like to talk about. So what we are trying to capture is representations that try to capture the core of interaction. So they're almost like an approximation of the sufficient statistics needed for this multi-agent interaction. And we are putting a set of priors when you're learning those representations. Specifically, the prior I'm putting in here is that these representations need to be low dimensional. And the reason I think they need to be low dimensional is that humans are able to do these tasks, like humans are amazing at doing these tasks. And I don't think they're capturing high dimensional belief representations. I really don't think like here, Alex is building this high dimensional belief representation over the other agent's policies. Like one thing I know about humans is that they're bounded rational. They're not going to be able to capture these high dimensional beliefs. So the assumption that we're putting in here is that there exists a low dimensional representation that captures the interaction. And if I learn that, I can also capture the interaction and I can coordinate better. And I can even use that for better adaptation when I think about coordination changing over time, like Bob and Alex getting better at the construction task. And that brings me to this work that I'd like to talk a little bit about. And after that, I'm going to switch to Erdem to discuss about learning, talking about learning from interactions. All right, so the setup that we started looking at was a robotic setup. So we have two robots that are trying to play a game of air hockey with each other. I have a robot that I'm calling an ego agent. So this is a robot on the left. And I have another robot that I'm calling the other agent. The reason I'm calling it other agent is that the paradigm I'm talking about could actually work in both collaborative and competitive settings. So there's nothing special about this that could only work in collaborative or only work in competitive settings. So I don't want to call it an opponent or partner. I'm just calling it other agent. And we're getting these two arms to play a game of air hockey with each other. And this other agent, the policy of the other agent is actually high dimensional, right? The robot arm has 7 degrees of freedom. Each degree is a joint angle that lies in a continuous space. And the thing that this ego agent is really observing is even not that, but like if it were to observe the actual actions of the robot arm, it would be high dimensional. And if it wanted to do belief modeling over that, it would be over a very high dimensional space. But at the high level, I'm telling you that this other agent is pushing the puck towards the left or right or the center. This ego agent doesn't know that, right? Like doesn't really like even observe that. But I'm telling you guys that the other agent has this policy that is kind of has this low dimensional structure into it. It's pushing the puck to the right, center, or left. Okay? And what the other agent observes instead is a trajectory. It's a sequence of states, actions, and rewards, states of the world, its own actions, not even the actions of the other agent, but it also sees the reward. If I was able to block the puck, or what is my distance to the puck? And then that is what the ego agent observes over some particular horizon, some particular episode. Okay? And then this other agent, as I was telling you, right, like it has kind of this high dimension, like this like low dimensional representation. Its policy is pushing the puck to the left or center or the right. And the way it decides is based on what happened in the previous time step. So if the ego agent was able to block the puck, it's going to push the puck towards a different direction. So it has a very simple policy. But again, ego agent doesn't really observe that. So what we are proposing here is to get the ego agent actually learn this high level representation that I was talking about. So the way we can do that is we can look at a previous sequence of trajectory, an episode at time step k-1, and try to encode that into a low dimensional representation, ZK here. And I'm calling this ZK a latent strategy or latent intent because it's a low dimensional representation of what the other agent is trying to do. This is what ego agent thinks the other agent is going to do next. Is it going to push the puck to the left or center or the right? Like that notion of center, left to the right and right is the thing that's going to be captured by ZK. And how do we actually ensure that that will be captured by ZK? Well, we're going to try to decode this ZK into the next trajectory, into a prediction of what will happen next. So our loss function, our learning objective here is really a prediction loss. We look at a previous trajectory, we try to predict what will happen next. And for me to be able to predict what will happen next, I need to know the state, I need to know my policy. Those are the things that I already know. But I also need to know how the other agent is acting and how the other agent is influencing the state. So I need to know the policy of the other agent. So that is the thing that is going to allow me to reconstruct, or not reconstruct, really predict future. But I also enforce that representation to be low dimensional. So I capture like the sufficient information, the sufficient statistics about the other agent through this representational learning component. Okay, so that's really the key idea of this work. Okay, so once I have that representation, I can use that representation however I want, right? Like I can use that in any planner. I can do model predictive control with that representation, or I can have any other controller that uses that representation. What we decided to do was we decided to do reinforcement learning. So instead of our, for our planner, we decided to have a reinforcement learning component that tries to come up with policies for our ego agent. And this reinforcement learning component is maximizing the expected return, but this expected return is dependent on the representation that we have learned so far. This is a representation of the other agent, the latent strategy of the other agent. And this algorithm is called Lily, Learning and Influencing Latent Intent. And the idea of it is to iteratively train a reinforcement learning agent that's trying to come up with a policy for the robot, and a representation learning component that's trying to capture what the other agent is trying to do. And together, like with this iterative training, you're able to build policies that allow us to react to the other agent. Okay. All right, so let me show you how this works in practice. So if I were to use, let's say, soft actor critic, like let's say state-of-the-art reinforcement learning, soft actor critic, after 4 hours of training, it's able to learn how to block a puck. It generally just learns blocking a puck. If it goes towards one direction, it's able to block the puck, and so it learns how to do that. But it doesn't model the other agent, like it doesn't capture a representation of the other agent. And because of that, it always goes towards one direction. So for example, in this case, it always goes to the left. And in terms of success rate, soft actor critic is around like 40% success rate. It always blocks to the left in this case. And around 40% is it should be like really 0.33 like success rate, but it gets lucky like 40% of the times, and it's able to block the puck in those settings. But if you're using our algorithm, Lily, after 4 hours of training, Lily is able to actually predict a model of the other agent, like predict this latent strategy, a low dimensional model of the other agent. And based on that, it's able to block the puck, and it gets a success rate of around 90%, which is pretty good. Okay. All right, so that's all great, right? So I've talked about learning representations. This is, one can really think of this as an orthogonal perspective to that game theoretic modeling, right? Like in these more reactive policies, right? We are learning a low dimensional representation, and that captures the model of the other agent. And using that, we are able to train a reinforcement learning agent that can coordinate. But one interesting point that I also want to mention here is that I can go beyond reacting to other agents. I can go beyond a simple coordination. And specifically, what I can do is, if I optimize for a long horizon objective, I can maximize, for example, expected return across multiple interactions, and that would allow me to influence other agents. So not only I can coordinate with them, but I can get them act in specific ways that are useful for me, that can help me, like as an ego agent, to play better, or like win the game more, get higher rewards, and so on. And I want to briefly talk about this idea of influencing. So here, the way we are doing influencing is by just considering a long horizon objective. So instead of considering my original objective, I'm now considering it across multiple interactions, and that could get me higher rewards. So as an example here, what we are able to do is we are able to influence the other agent, this robot, to push the puck more often to directions that are useful for us. So here we are artificially making it so if the ego agent goes to the left, it gets higher reward as opposed to going anywhere else, like going to the right or blocking the puck to the center. So my ego agent really wants to go to the left because that way it gets higher reward. Okay? So Lily, with influencing, after 4 hours of training, it's able to actually get the other agent to more often push the puck to the left as opposed to any other direction. So one interesting point is that with influencing, success rate, it's around 90%. It's actually not worse, which is nice. So no matter where the puck is pushed, with influencing or without influencing, this representation is really helpful for us to figure out how to block the puck. So we get a success rate of 90%. But the interesting thing is that with influencing, I'm going to get the puck more often to the left, as opposed to towards the other directions like middle or right. And with no influencing, right? Like we are not affecting like how the other agent is playing. So because of that, we get the puck like 33% of the times, like towards any of these other directions. All right, so that's all great. And I think this idea of influencing has a lot of potential. So we saw that even earlier in the setting of, in the driving setting that I was talking about, right? Like if you go back to this slide, this driving setting, this game theoretic type of model allows us to think about influencing. When my car was nudging in front of this other driver, it was modeling the other driver, but it was also modeling the fact that it can influence the other driver to slow down, right? Like if this car was going like 20 miles per hour, if a car cuts in front of it, like it's not going to go 20 miles per hour anymore, right? Like it's going to reduce its speed to like 5 miles per hour. And the reason is it also doesn't want to collide. There is like this objective of collision that it cares about. And this vehicle, by knowing that, it can actually like manipulate the other agent to slow down, and that's pretty interesting. And we kind of like see that this other paradigm, with the air hockey paradigm, and in this air hockey paradigm, right? Like the thing that we get is that more the puck is more often pushed to the left. That is the way of influencing that we are seeing here. Okay? All right, so that's all great, but one other interesting point is that influencing can allow us to solve reinforcement learning problems in a more effective way. So in a recent work, I want to very briefly mention this, and then I'm going to switch to Erdem. In a recent work, this is a Coral 2021 work. What we are looking at is influencing to actually help with reinforcement learning and multi-agent reinforcement learning problems. If you think about multi-agent reinforcement learning, one of the biggest challenges in multi-agent reinforcement learning is the non-stationarity of the environment, specifically the non-stationarity of the other agent, right? Like in multi-agent reinforcement learning is notoriously harder than single-agent reinforcement learning, because you need to model what the opponent is trying to do, what the other agent is trying to do. And this idea of learning latent representations is trying to like have a more efficient way of capturing that. Like what I've talked about so far with Lily is, let's try to learn representations, because that is a more effective way of capturing that non-stationarity. But the interesting thing is with influencing, maybe you can remove that non-stationarity like fully, like maybe you can reduce that non-stationarity. So a fun example, this is a mock-up example, is imagine that you and some other agent, you're trying to clean a house. Okay, so you and your partner, you're trying to clean a house. And that can be a very difficult task. Like if you're trying to figure out how to clean the house, you need to learn that. But you also need to learn what my partner is trying to do. Like, how is my partner cleaning the house? And that can be pretty difficult too. So instead, like what you can do is maybe you can lock up your partner in a room and then go and learn how to clean the house as a single agent, instead of you trying to model everything about your partner. So maybe like that would allow some sort of task allocation that would make the task easier. And we're using exactly that insight. Maybe we can learn this latent representation and then use the latent representation to stabilize the other agent, to like fix the policy of the other agent. And that could potentially help with reducing non-stationarity. And that's actually something that we're showing in this work with this algorithm called SILI, stabilizing influencing latent intent. And with SILI, we can actually show that if you separate the task into just doing the task and stabilizing the partner, that could actually help you achieve the task more effectively. And I'm actually really excited about this idea because it does have like real implications in robotics. Like if you think about a lot of bimanual tasks, like using two arms to do various types of tasks, like in a lot of these types of tasks, one arm is solely used to stabilize the environment. Like imagine that you're trying to cut a steak. Like it is really difficult to cut a steak with one arm, like the steak flies. So you use the second arm to hold the steak. Why are you holding the steak? Because by holding the steak, we have a much simpler problem to deal with. Like we don't need to worry about the dynamics of the steak, like flying around. It's actually stable. Like the steak is going to be stable, and I can easily predict the dynamics of the steak. And then my other arm can be focused on the act of cutting. So you're basically trying to use a lot of ideas around silly in actually like doing bimanual tasks like food manipulation and cutting a steak. And this kind of relates to some of our work in the space of assistive robotics that I will very briefly mention at the end after Erdem's bit. But let me just summarize and switch to Erdem. So the key takeaways of this section that I've talked about is the fact that human partners or other agents, they're often non-stationary. And this can be represented by low-dimensional latent strategies or latent intents. And Lily here anticipates partners' policies using these latent strategies, and it allows us to react or even sometimes influence other agents. And Silly, this other follow-up that I was very briefly talking about, basically uses influencing and takes influencing to another level to stabilize the other agent, to reduce non-stationarity and help with solving some of these problems. Okay. All right, so that's all great. So, oh, I moved to a wrong slide. I was going to go here. So far, I've basically talked about this idea of learning and influencing interactions. But in the second part of the talk, what Erdem would like to talk about is this idea of learning from interactions. So if you think about it, like if you have a robotics agent, right, that robotics agent can learn from human demonstrations, but it can also learn from many other sources of data and leverage those different sources of data to actually be able to coordinate and to be able to learn various types of policies. All right, so with that, let me stop sharing and I'm gonna let Erdem to take over.
Okay, thank you, Dorsa. So as Dorsa mentioned, like we want to learn humans' underlying reward functions through some interaction. And our insight here is that it might be difficult to get data from humans, but humans leak information everywhere, and maybe we can be a little bit smarter about how we are collecting data from them. Let's think about a robot trying to do a task like picking up an object, as in this picture. Like ideally, one way to achieve this is to write out a reward function and ask the robot to optimize it. But this is often difficult because these reward functions are not easy to design by hand. And another way of doing this is to have a human provide a set of demonstrations on the robot and ask the robot to try to imitate this human as closely as possible based on their demonstrations. This idea is often known as imitation learning or learning from demonstrations, and it has been around for more than 2 decades now. And most of the field has been looking at this idea of learning reward functions from expert demonstrations, where we assume access to an expert who can provide us with a large number of demonstrations that are almost perfect. And then the robot can basically imitate those demonstrations, and that's it, we are done. But in reality, we don't really have access to these perfect expert demonstrations. If we want to train with humans, we are not going to be able to ask the humans to provide us that much data or provide us near optimal expert data. In reality, we have access to a lot of offline suboptimal data or observations, like YouTube videos of people doing things, and that's not necessarily expert data. Or we have access to other types of data, like language instructions or narrations. And in addition to that, we have access to a variety of other data sources. Like as an example, we can think of pairwise comparisons or rankings, where we would ask humans to rank a bunch of different trajectories instead of asking them to provide us demonstrations. And if you think about this robot is an embodied agent in the world. I can actually move it around and I can provide physical corrections. So the thing is, we often do not have access to expert demonstrations, but we have access to many other types of data. And we can actually be much smarter about how we are collecting data from these different sources. And that's the insight we are trying to use here. And in this talk today, I'm going to specifically talk about pairwise comparisons and more generally rankings. So how can we learn from them and how can we be smarter about how we collect data? What do I mean by that? So imagine I have a robot, and instead of asking a person to come demonstrate how they would get this robot to do a task, I can ask this person, like, well, I'm going to show you 2 different trajectories, trajectory A and trajectory B, and you just tell me which one you prefer. And based on the human's response to that simple binary question, I'm going to get some information about the underlying reward function that the human wants the robot to optimize. And for now, I'm going to assume that this reward function is a linear combination of a set of hand-coded features. So the reward is basically parameterized with some theta, a vector of weights, which is multiplied with a feature vector, the features of the trajectory. As an example, imagine that we have only 3 features. So theta lives in this 3-dimensional space, and each of the points here represents a set of parameters. And there's a true reward parameter, a true theta in this space. And what I'm trying to do is to figure out what that is based on querying the person and asking them pairwise comparison queries. But every question that I would ask to the person here would generate a separating hyperplane. And the human's response to that question is going to basically tell me which side of the hyperplane they prefer. But humans are noisy, so I'm not going to fully trust their responses to my pairwise comparison questions. And because of that, I use a noise model where I don't completely remove the wrong side of the hyperplane. Instead, what I do is I end up reweighting these points based on the noise model and give more weights for the preferred side of the hyperplane. Okay, so this is just one query. And I make one query to the person, and it corresponds to the separating hyperplane. The interesting question that we are excited about here is, how can we ask a sequence of such queries? Like, we want this sequence to consist of the most informative and diverse queries, and based on those, we will learn the human's underlying reward function as quickly as possible. So the way we formulate this problem is as an active learning problem, where we would like to actively generate a set of scenarios on which we can ask the person what their preferences are. Or more formally, what we are trying to do is we are trying to optimize an objective over a set of scenarios, a set of trajectory features. And this objective corresponds to an information theoretic objective. For example, that could be mutual information, or could be based on the determinant of some repulsive point process. Or in this case, it's about the volume we are removing from the hypothesis space. So the question we are asking is, can we find a query that maximizes the minimum expected volume that's going to be removed from the hypothesis space? And this is basically ensuring that every question we are asking is going to be informative. Every question is going to give a lot of information about the reward function. Of course, this is all subject to the fact that these queries are going to be realistic and we can actually run them on a real system, and they're feasible. All right, so at every time step, I'm going to run this optimization, and based on this optimization, I'm going to actively generate a new query to the person, and they'll give us a response, and based on their response, I'll be able to learn the reward function. Here are actually some results in a very simple 2D driving simulator. So basically, after 0 queries, I don't really know what to do. But after 30 queries, my vehicle learns how to keep the heading straight. And finally, after 70 queries, the car learns how to keep the heading and then avoid obstacles, etc., to eventually drive in this simulator. And I'd like to emphasize that this is actually pretty impressive. I didn't get any demonstrations from the human, and there were no expert demonstrations going on here. I just asked 70 simple binary questions to the user, and based on that, I'm able to get this vehicle drive in this simulator. Okay, so we now have a way to actively learn unimodal linear reward functions. In learning from pairwise comparisons, there has been many works that focus on learning unimodal functions, including the work that I've just described, and many others that study different acquisition functions or for active querying. But what if the data come from multiple users who have different reward functions, and our robot doesn't know any of them? It doesn't even know who provided the data. But although there have been many works for the unimodal reward functions, learning multimodal rewards from comparisons, it was not studied. Let me explain why multimodal rewards are more difficult with an example. So let's consider this scenario. Here we have the red autonomous car who wants to make a left turn. So it starts turning, but then it realizes the blue car, which is coming from the opposite direction and was previously occluded behind the red truck. Depending on its policy, the autonomous car may make different decisions now. If it's using a reward function that it learned from a timid driver, the car may stop and give way to the blue car. it could avoid an accident in this way. Okay, this is our first scenario. As a second scenario, we could think of a case where the data come from an aggressive driver. And in this case, the autonomous car could try to complete its turn before the blue car reached the intersection. And this is another way of avoiding the collision. But what if autonomous car was trained using data from both drivers? In such settings, we cannot really use standard learning from comparisons techniques because the car would have an accident while trying to find a policy that's close enough to both drivers. We investigated this problem on a home robotics task where we can safely collect some data. And here the fetch robot wants to learn how and which shelf to place the banana. Perhaps a user comes in and says they prefer the first trajectory over the second trajectory. It's no problem, fetch can handle it because it knows how to learn unimodal rewards. But if a second user with different preferences shows up, then fetch will fail. And in fact, it's doomed to fail. Let me explain why with a numerical example. So we have two trajectories, psi1 and psi2. This first user comes in, and let's say their reward for the first trajectory is 2 and 1 for the second trajectory. Following prior work, we model the user's comparison response with the softmax model. So the probability that the user chooses a trajectory is proportional to the exponential of its reward. This model would give us these probabilities. Now, we also have the second user with different rewards and preferences. And let's say the first user provides 20% of the data and the second user provides 80%. Combining these, our robot would observe a data set that's 24% in favor of the first trajectory and 76% the second trajectory. Now, the problem is, I can come up with another pair of users whose rewards and preferences are different, such that with different data frequency, they also provide the same data. So our robot is only observing these data at the end. So from its perspective, these two settings are just indistinguishable. It would have no way of identifying the underlying true rewards. In fact, researchers in ranking theory proved that you can always construct examples where learning multimodal, even bimodal rewards from pairwise comparisons is impossible. So are we done? Well, no, because we can think of some generalizations of the problem. Specifically, instead of learning from pairwise comparisons, let's say we will learn from rankings of multiple trajectories. So in this work, we're like solving the problem of learning multimodal rewards using rankings. To reiterate, the robot is going to show multiple trajectories to the users, and it will ask them to rank these trajectories from best to the worst. We will have multiple users, each with their own reward function. And again, following the prior work, we will assume these rewards are linear functions of some known trajectory features. For example, in this task, the features could be the speed of the robot, which shelf it places the banana, etc. And the ranking query will then be answered by one of the users with some unknown probability parameterized by alpha. Let's say the first user is going to respond to this query. Our robot, however, doesn't know this. Okay, so how does the human answer? He will first noisily select his best option. So we again have these probabilities that are proportional to the exponential of the rewards. And the user's top choice will be a random sample from this distribution. Okay, next, he will noisily choose his second best option. Now the first option has already been selected, so we drop that. And the user's second top choice will be a random sample from this remaining distribution. Similarly, the process will repeat for the third best option. And finally, there will be only one option left, which is the user's first option. So this response model that I described for a single user is known as loose choice axiom, and it's a very standard model for rankings done by humans. Eventually, what our robot observes is only this ranking. It doesn't know which user gave this ranking. It doesn't even know the probability that this ranking comes from this user. So from our robot's perspective, we have this user model. It doesn't know alpha, but it observed the ranking. It will start with a prior over both alpha and the user's reward functions. It will then use Bayes' rule to update its posterior based on the ranking it observed. Note that this likelihood term here is just the response model that I described. Like mathematically, I can expand it as follows. First, it's either the first user who responded or the second user. And we already know the first term here and here. It's the probability, the data frequency probability based on alpha. We can also expand the ranking probability conditioned on the user. This is again the loose choice axiom. And we repeat that for the second user too. So we have this full model for the likelihood probability. And our robot will perform this posterior update for all ranking data it has. At the end, it will learn all the reward functions. In fact, it will even learn the data frequency parameter alpha. Let me show you some simulation results. On this fetch robot task with bimodal data, we observed that modeling the reward as a unimodal function failed terribly. There were many outliers because the robot was trying to come up with one mode that explains all the data. To get nicer graphs, we had to also plot the median error. On the other hand, modeling the reward as a multimodal function using our mixer model gave much better performance and learning, both in terms of mean and the median. And the results were similar on OpenAI's Lunar Lander, where we again simulated a bimodal reward. One question that's still remaining, though, is how the robot chooses which trajectories to show to the users. And for this, we again developed an active querying method, similar to the volume removal approach I talked earlier, to increase data efficiency. Our idea here is to maximize the mutual information between the reward and the user's response given the query. This has been studied before for the unimodal case, and it's very similar in the multimodal case. We now need to maximize the mutual information for both the rewards and the data frequency parameter alpha. I'll skip the derivation, but this is the final optimization problem we ended up with. Here, all probability terms are easy to compute. They're just our response model. What is more tricky is these expectations, because they require sampling from the distribution of alpha and rewards, which is multimodal in this case. In the unimodal case, the most standard approach is to use Metropolis hastings for this sampling, but it's problematic in this multimodal case. For example, let's take this distribution with two modes, and Metropolis hastings would start with a random point, and it would just remain around the mode that point is closest to. It wouldn't be able to discover the other mode in a reasonable amount of time. To handle multimodal distributions, we simply run multiple chains of Metropolis hastings. So let's say we start with these three random points and then run three independent chains of Metropolis hastings. As long as we have enough chains with a good coverage of the distribution support, we will have samples all around all the modes. So going back to our optimization problem, these expectations can now be approximated using these multi-chain Metropolis hasting samples. The only remaining part is how to solve this optimization problem. In the case of pairwise comparisons, looping over all possible queries might be feasible, but it's not here because queries consist of many trajectories now. So we used simulated annealing instead to solve this problem. In the end, we compared this information gain-based active learning with random queries and also the volume removal-based active learning. And we observed in simulations that it gives the information gain-based method gives the best results on both the fetch robot and the Lunar Lander tasks. It increased the data efficiency. And when we look at the policies optimized with respect to the learned rewards, we again saw information gain outperforms random queries. And finally, we designed an online interface to conduct some user studies. In this interface, multiple people provided anonymous feedback to the robot by ranking 6 trajectories from best to the worst. Let's watch the end result after 10 random and 10 information gain optimized queries. As you can see, both robots learned the preference of the first user, but the robot who makes random queries instead of information gain optimized queries hasn't properly learned the second user's preferences yet. It's still dropping items out of the shelf, as you can see here. We also looked at quantitative measures, such as the predictive power of the learned multimodal rewards. In both fetch robot task and the lunar lander task, information optimized queries gave the best results. All right, so going back to this picture, we now know how to relax the unimodality assumption. And the other fundamental thing that I've been assuming is that the robot is trying to optimize a reward, which is a linear function of a set of features, or a mixture of linear functions in the multimodal case. But in reality, these reward functions are not always a linear combination of a set of features. Here's an example of that. Imagine we again have this robot and we wanted to play a version of mini golf. We wanted to get this ball into one of these targets. And I want to do that by using preference-based learning, where I have a human teacher and then I can show different trajectories. I'll ask the user which one of these trajectories they prefer. And based on that, I'm going to figure out what they want. The problem in this setting is if I want to assume a reward function that's a linear combination of a set of features, I'm going to have a lot of issues with the feature design. And in general, if you look at prior work where they assume a reward function that's linear in a set of features, they usually have statements that kind of look like this. They say, well, let's pick a feature that is an exponential of minus C4 times D4, and C4 is equal to 3. And you might ask, well, where does that come from? Like, how do you know C4 is equal to 3? That sounds like magic. Or you might have other features that seem pretty magical too. So you have another exponential here, in fact, with some squares now, and then you pick C2 to be 7 and C3 to be 3. And these are hyperparameters, right? They're highly tuned, and in general, they're very well designed to make sure everything runs okay. And that basically tells us that designing features might get extremely difficult here. One question you might ask is, why are we even designing features? Why can't we just use neural networks? The whole point of deep learning was to get rid of feature generation and be able to use neural networks to automatically generate them. But remember, I cannot train with humans in the loop if I'm using deep learning, because that's just not going to scale. When I have too many parameters, even if I'm doing active learning, it's going to be too difficult to actually get enough training data from humans. And the other issue here is that if I pick simple features, if I don't want to do all this feature engineering, a lot of times the robot won't be able to capture my objective. So let's say my objective here is to hit the ball to one of these targets, and I pick these features to be shot speed and shot angle, which would, by the way, completely characterize the trajectories. But with these features, I'm going to be able to target only the corners of this space. I'm not going to be able to hit any of these targets, actually, because the linearity assumption will cause the robot to either minimize or maximize its shot speed and shot angle. On the other hand, if I model the objective as a nonlinear function of these features, even if my features are simple, I should be able to hit the target I want. So basically, our insight here is to not have a deep neural network and not have a linear function of features, but instead be able to model a nonlinear function of features that's able to actually cover this full space and differentiate between different targets. So in particular, we are going to use Gaussian processes for this. Let's now look at how our framework works. The robot will keep a Gaussian process as a model of the human's underlying reward function. And using this model, it will generate the query that will give the highest expected information gain. Of course, I'm skipping out of mathematical details here. And after it decided to query, it will show it to the user, the trajectories to the user, and the user is then going to respond to this query. We will store this response in a database. And here we are again using a noise model for human responses, just like we did in the linear reward case. Like depending on how close the rewards are to each other, we produce probabilities that are close or different. And using this noise model, the responses in the data set will give us a likelihood function, which we can use for fitting the GP. It actually doesn't fall into the class of GPs, but we can use, for example, Laplace approximation to cast the posterior as a GP. And the process will then repeat using this new posterior. Okay. Let's first start with looking at some queries made to the user. So this is from an actual user study. Here, I'm showing you an information optimal query where we model the reward as a linear function of features. As you can see, the robot hits the ball to the boundaries because it believes one of the extremes must be optimal. However, we can significantly improve expressiveness of our queries if we model the reward using a Gaussian process. As you can see in these video clips, the robot can now hit the ball to the different regions. So the GP modeled reward enables the robot to explore a broader range of trajectories. Okay, so those were some example queries. Now let's go back to our diagram and look at the learned policies, like the policies the robot learns after making some number of queries. Again, the linear reward model is unable to generate a good shot, but the GP model efficiently learns the reward function and achieves hitting the desired target, the blue ball in this case. So the mini golf, it's a toy example, but there are also many real settings where we need to model the utility as a nonlinear function. For example, we showed that one can use preference-based learning enhanced with ordinal feedback to do exoskeleton gait optimization. Here, each gait is parameterized with pelvis pitch, pelvis roll, step length, and step duration. We need to model the human's preferences or reward function as a nonlinear function because humans do not necessarily like the maximums or minimums of these parameters. And perhaps more importantly, some gaits may feel unsafe for the users, and we need to avoid that even while we are learning their preferences. With our preference-based GPU regression model, we were able to both model and ensure this safety constraint and learn personalized, like nonlinear utility functions at the same time. And this is an important step for the science of walking, as we can now better understand the gait preferences of the users. All right, just to summarize, we have been talking about using these pairwise comparisons and rankings as a way of learning reward functions. And in general, I want to emphasize again that people leak information and they give us information in different forms, such as physical corrections or pairwise comparisons, and we can try to learn from these different sources of data. With that, I would like to pass it back to Dorsa.
All right, so I'm not going to share screen anymore. I just wanted to wrap up and summarize what we have talked about so far. So just to summarize, right? So the way I started talking about this problem of interaction was using learning for better interaction. So we talked about learning representations, low dimensional representations that can help us coordinate and collaborate better or even influence agents. And in the second part, just to summarize, what Erdem talked about was learning from interactions. And he specifically talked about pairwise comparisons and rankings as a particular form of data that we could collect from humans, and problems such as nonlinearity or multimodality of reward functions when we try to learn these types of models from this type of data. So in general, I think learning from interactions for interactions are pretty interesting problems, lots of open questions there. And with that, Erdem and I can take any questions.
Thank you very much, Dorsa and Erdem, for the nice and interesting presentation. So if there is any question, please